All right, let's just jump right in with a little thought experiment. I want you to forget everything you think you know about geology. Seriously, for the next few minutes, we're not going to be scientists. Nope. We're going to be forensic engineers. And we're treating planet Earth like, well, like a piece of incredibly complex hardware. Or maybe, just maybe, like a crime scene.
I mean, think about it, right? We are wired to recognize design. If we sent a rover to Mars and it stumbled upon a perfectly spherical humming metal orb, NASA wouldn't just call that a fascinating geological formation, would they? No way. They'd say, someone built this. So here's the big question. Why, when we look at our own planet, a planet with a nuclear core, its own force field, and a satellite placed with impossible precision, do we just shrug and say, oh, that's just a random formation? Okay, so our investigation, it's going to start with Exhibit A, what looks like a perfect coincidence, one that involves our sun and our moon.
So you know total solar eclipses, right? Beautiful. Awe-inspiring. But if you're looking at this with an engineer's eye, it's not just a pretty show. It's a statistical impossibility that just screams for an explanation. I mean, what are the odds? How do these two completely different objects line up so perfectly, just for us, from right here on the ground?
Well, the answer, believe it or not, comes down to one single number, 400. You see, the sun is about 400 times wider than the moon. Okay, makes sense. But here's the kicker. It's also almost exactly 400 times farther away. And that perfect, mind-boggling ratio is the only reason our tiny moon can perfectly block out that massive, blazing sun.
To really get a feel for this, try this. Imagine holding up a quarter and trying to use it to perfectly block out a giant searchlight that's a mile away from you. The angles, the distance, the geometry, it all has to be absolutely perfect. That isn't luck. That's sniper-level precision. So, if it's not just a cosmic lottery win, what is it? Well, this leads us to a pretty radical theory. What if the moon isn't just some random rock that got caught in our orbit? What if it's a functional component, like a massive gyroscopic counterweight, specifically designed to keep our whole planet spinning stably without wobbling all over the place? And if that's true, well, that opens up a whole new can of worms, doesn't it? I mean, think about it. If the moon is a stabilizer, you have to ask, what kind of ridiculously powerful engine would need a counterweight that big? To find that out, our investigation has to go deep. We're talking deep inside the planet, right to its core. So the story you usually hear is that the core is kind of like a hot potato, right? Just this leftover heat from when the planet formed, and it's been slowly, passively cooling down for billions of years. But the engineer's view? Oh, it's completely different. It's not a passive cooling remnant at all. It's an active, self-sustaining nuclear fission engine, a flywheel, that's constantly generating its own incredible power. And look, for a long, long time, we were just piecing together these little clues. Back in 1906, we finally proved the core was even there. Just 2 years later, some were already kicking around the idea that it was like an internal sun. But the real smoking gun, the piece of evidence that totally blew that cooling potato model out of the water, that didn't show up until 1996. And this is where it gets really wild. Scientists discovered that the solid inner core is actually spinning faster than the rest of the planet. It's lapping us. Think about that. A passive, cooling chunk of metal, it just shouldn't do that. But a powerful, detached engine generating its own rotational energy? Well, that's exactly what you'd expect to see. Okay, so if you've got this massive engine running deep underground, it stands to reason you'd need some, maintenance systems up here on the surface to keep everything running smoothly. And this is where we have to completely rethink what we call natural disasters. Nature is incredible. It can evolve a bird over millions of years. But nature cannot evolve a combustion engine. And that's because complex, interconnected systems don't just happen by accident. Take a volcano. It's a ridiculously complex pressure relief system. You can't have half a volcano. It's not something you can build piece by piece over eons. It either works or the entire planet goes boom. It's an all-or-nothing piece of machinery. So when you look at it through this engineering lens, plate tectonics suddenly stops looking so random. It starts to look like a highly organized, systematic recycling process. You've got these subduction zones that are basically ingestion ports, pulling in the old, dirty, carbon-heavy crust. The mantle acts like a giant processor, melting it all down. And then, voila, Clean, new crust is pushed out somewhere else. It's like a giant planetary self-cleaning oven for the hull of the ship.
So suddenly, these things we call natural disasters start to look a lot more like system maintenance. Volcanoes, they're just thermal pressure relief valves. Those giant, mysterious, dense blobs deep in the mantle, maybe they're just lead ballasts, keeping the whole machine stable as it spins. And earthquakes? That's not the sound of the planet falling apart. That's the sound of the ship staying alive. All right, any well-designed ship, especially one carrying, well, us, needs a protection system, right? A shield. So, for the next piece of our investigation, we're looking at the planet's active defense system, its very own force field.
And this is a really important point we need to get straight. We tend to think of the core as our planet's heater, but that's not quite right. We get plenty of heat from the sun. No, according to this engineering model, the core's #1 job isn't to keep us warm. It's to generate the shield that protects us from that very same sun.
And if you want to know why that matters, just look next door. Look at Mars. It probably had a thicker atmosphere once upon a time. But then its core cooled down, its shield failed, and poof, the solar wind just scoured its atmosphere away. That shield is literally the only thing standing between us and becoming another cold, dead rock like Mars.
And this shield, it's not some passive thing. It's being actively generated all the time. It's created by the different spin speeds of the solid core, the liquid outer core, and the crust, all moving against each other. It's a dynamo effect, which basically turns the entire planet into a giant electromagnet. And that's what creates this incredible, active, protective energy bubble that we're all living inside right now.
Okay, let's step back and look at the evidence we've gathered. Exhibit A, a stabilizer satellite placed with sniper-like precision. Exhibit B, a super-rotating nuclear core acting as a power plant. Exhibit C, automated self-cleaning and maintenance systems. And Exhibit D, an active self-generating deflector shield. So, what's the verdict?
You know, the idea that this all happened by chance, it's kind of like what you might call the Powerball fallacy. Winning the lottery once is incredible luck, sure. But Earth didn't just win at life 4 billion years ago. The real miracle is that it has stayed operational every single day since, for 4 billion years, surviving every cosmic catastrophe you can imagine. That isn't a winning streak. That sounds a lot more like a design feature. And that brings us to the final and maybe most important thought. Imagine you're out in the middle of the ocean and you find this huge, advanced ship. The lights are on, the engine is running, the kitchen is literally cleaning itself. You wouldn't stand there on the deck and ask, wow, I wonder how the ocean currents and the waves managed to build this thing. No. You'd ask a very different question. Where are we going? And maybe, just maybe, that's the real question we should be asking about planet Earth. There's this constant, low-frequency electromagnetic hum that our planet gives off. It's about 7.83 hertz. It's called the Schumann resonance, and people sometimes poetically call it the planet's heartbeat. But looking at it through this new lens, this investigative framework, maybe it's not a heartbeat at all. Maybe it's something else entirely. Maybe it's the quiet, persistent, idle noise of a massive machine, just waiting.